about that from, and I'm not going to ruin the pronunciation of the institution by trying, the Pontifical Catholic University.
That's
right?
That's it.
Thank you
very much. Thank you for the introduction. Am I too nervous, or is it a little cold here? I don't know.
It's
cold.
It's cold. Let me just open the presentation. So I got the back and forth button here. So, as he said, I'm Thiago Alves. I'm from Pontifícia Universidade Católica in Minas Gerais, with my accent. And I'm very pleased to be here with you this afternoon and share my project with you. Is it okay? My voice is still good volume. Okay. So I would like to start with a date. I know that most of us are all engineers, and history is not a very big deal for us, but what happened in 1830? There's something good that happened in 1830 that changed the world, that changed the way we act and we think, and what happened was Industrial Revolution. Industrial Revolution, it marks a major turning point in our human history. It changed the way we look at things, the way we act, and it brought many good things to our society. The Industrial Revolution marks a transition from a hand production to machinery production. And that's a good thing because it improved the quality, improved the efficiency of our systems. It also brought population average income growth, according to some researchers, and product price reduction. Since we are producing now in mass production, high volume, the products are now costing a lot less. If you look at data from the prices of cars, for example, for 80 years ago, you'll see that they are very expensive, and now everybody can afford to have a car. So if we take a look at this map is just showing the level of industrialization and of development of a few of the countries in the world. And the blue area are the countries that are more industrialized. Against the red area, there are the countries that are less industrialized. If we compare this map to this one that shows the Human Development Index, we will see that usually the countries that are more industrialized have a better Human Development Index. So what I want to say with this is that industrialization often brings development, and development brings a better quality of life. So people are having better lives after industrialization. But unfortunately, I came from a country that are a less developed country, that are being a developing country. We have some barriers for industrialization. And I would like to discuss here about two of these barriers. The first one is knowledge. Knowledge is a big problem for less developed countries since they don't have a good access for education. Even on schools and colleges, they don't have that much access to labs or to good teachers or to good education. And this sometimes brings the other problem. Since we don't have access to knowledge, we can't build our own machinery, our own equipment for industrialization. So we need to buy them from the other countries, and that's very expensive. So that's the second barrier. The second problem is that the cost is very high for industrialization. I wanted to create a project or something that could break these two barriers and that can bring industrialization to places that wasn't available before. And so I created the OpenPLC. It's an open source industrial controller. For those that are not familiar to PLCs, PLCs stand for Programmable Logic Controller. It's like a special device, electronic brain that goes inside a machine, and you put your code on it, and then it can control the machine according to the code you put on it. And it's largely used on industry for automation. So actually, when we engineers face the PLC, for us, it's just like this black box with a question mark on it sometimes. But this black box, it's a device we buy for a very high price on the industry, and then we just connect it to our computer and we program it according to the standardized language they have for programming. And then we put this thing on a machine and we expect it to control the machine the way we want. So that's automation. The problem with this is that we don't know what's inside. We don't have access to information about how the system works. We just use it. So my project came to open this black box and give access to everyone. Everyone can know and can share information that is inside a PLC. So it's the first open source, fully open source programmable logic controller. While I'm trying to create this project, I look at few characteristics, common characteristics between different brands of programmable logic controllers on the market. And I figured out they all have usually the same aspects, the same characteristics. They must have a sturdy hardware to survive on the harsh environment of the industry. They also have a real-time software, which means that whenever you press that emergency button on your machine, you expect it to work immediately and to stop the machine, instead of waiting for updates from the App Store or anything else. They also have a standardized programming language, which means that engineers can work with the same kind of language between different brands and different kinds of PLC. I'll talk more about that later, but the standardized language usually is called ladder language. Ladder because it looks like a ladder, actually. But it was created on the 70s and 80s, and it's very similar to electrical schematics, so that electrical engineers can work with digital programming devices. They usually have network capability, so that you can connect the PLC with other devices on the industry. They can communicate and record data, and they must have protected inputs and outputs. Since engineers also make mistakes, it has to be protected to avoid short circuits, and also because the industrial environment is very harsh, it has to be protected to protect the sensitive circuit that is inside the PLC. And obviously it has to have expansion slots, so that it can just insert the cards, the expansion cards that you need according to your problem. So according to these characteristics, I tried to build this system. That's the OpenPLC. And it has some standards that are more widely available. For example, for programming, I used a USB port. And that's a big point for the OpenPLC, since most of the other brands of PLC use proprietary cables for programming, and they cost very much money, like even $100 or $200 for just a programming cable. Well, for the OpenPLC, you can just grab your printer cable and you can program it using your USB port. It has also the RJ45 connector for network capability, so you can connect it to the network on the industry, and it's capable of full TCP/IP stack, and also Modbus support. Modbus is an industrial protocol that it's widely used on many different equipments, so you can communicate with these equipments using Modbus. For the input voltage, it has a 24 to 30 volts power input, and an integrated regulator voltage for the electronics inside, and expansion slots. So OpenPLC is expandable. You can create your own kinds of expansion cards depending on your needs, and you can insert on the system, and they will work together with the other cards that are already developed. So let's talk a little bit about the OpenPLC architecture. I don't know if all of you are familiar to this kind of architecture, but I'll try to be simple and explain everything. This is the CPU card. It's the most important card developed for the OpenPLC. It has a processor to manipulate all data that is inserted through your programming. So it has a 16 million instruction per second processor. Sometimes it can be a little slow, but actually for this purpose it's not. It's very fast actually. And this CPU card has a RS-485 driver. RS-485 is a standardized protocol for communication, hardware communication. It's pretty old, but it's reliable, and people use it every day on industry because it's very reliable. It's very immune to noise and stuff. So this card has the master driver, so it can communicate to other expansion cards using this bus, the RS-485. A big point, it has a USB bootloader, so it's just like magic. You put your USB cable and you're ready to program. No extra additional software or anything different to program it. You just need the provided a ladder editor, and then you're ready to compile and upload your program because of the USB bootloader. This WizNet is an integrated circuit for Ethernet capabilities. It supports the full TCP/IP stack. So because of WizNet, I can have Modbus support and all other network support on the OpenPLC. And it has a small switch. It's a state selector that you can choose between running, stop, or automatic. That will assure you that your program is running when the switch is on running, and your program will stop whenever you need to communicate to the OpenPLC if you put the switch on the stop position. So the next board that I developed was the input card, and the input card is one of the expansion cards. It has 8 optocoupled inputs, so they are isolated from the external and internal circuitry. It has a processor, a simple processor, just to handle the communication with the main CPU card. Also, it has a driver for communication, but in slave mode, and overcurrent and over voltage protection. The other card that was developed is the output card. Similarly to the input card, it has 8 optocoupled isolated outputs, so they are relay outputs. It means that you can really control some big load on it, even DC or AC. It has a processor for handling the messages between the CPU card and the other cards. Also, a RS-485 driver and overcurrent and over voltage protection. And the last board that was developed is the bus board. Bus board is responsible for communicating, for connecting all the boards of the system. It has 8 expansion slots plus 1 slot for the CPU card, and it has also integrated a DC to DC converter, a regulated DC power supply to supply 5 volts to the entire system. And it was designed to have high-speed bus lines so that you can use that bus with high speed even to 1 megabit per second communication speed. So that's the architecture of the OpenPLC. That's the way it was designed. I just want to talk a little bit about the protocol I developed. I call it the OPLC protocol. This protocol is responsible for messaging, for communication between the different kinds of expansion cards and the CPU card. So it has to be simple, and it has to have a little overhead, because I wanted speed. So the messaging has to be very simple and straightforward with little overhead, so the cards can communicate rapidly, and I could have a very short scan time. Scan time in PLC language means that you are running through your program from the beginning to the end, and then you return to the beginning. So I can do the scan time in less than 15 milliseconds, even for large and complex ladder programs. And that was really good, thanks to the OPLC protocol developed. And it's also based on this master-slave communication, which means that never a card will start communication. It will always respond to messages sent by the main CPU card. The last point I want to talk about is about software. So PLC is not a PLC without a software. And I had to develop this simple ladder editor, but it's good for its purpose. It's a graphical editor. I promise it's graphical. Although simple, it works. And it's a standard. Ladder is a standardized language. So I had to follow this IEEE standard. And so it has all the functional blocks that are usual IDE for ladder programming has to have. For example, add, sub, move, greater than, less than, timers, counters. People that are familiar to programming, they're probably familiar with these things. But the ladder editor has everything that this language has support for. And as a plus, it has a code simulation. That's a big feature. It means that before you upload your code to the real hardware, to the real PLC, you can simulate it on your computer. So you can actually see the flow of the current or virtual current flowing through your contacts and see what actually is activated or deactivated. And then you can certify that your program is working as expected, and then you upload it, and everything will be as expected. And of course, it has the capability to compile and upload the ladder code through the USB port. And just a little explanation about this point. I said that 16 MIPS processor was fast enough for this, and it's mostly because the code is actually compiled to the platform. Usually PLCs nowadays, they don't receive this ladder code compiled. They receive like an XML file or something that they will interpret at runtime. So it has to be a fast hardware and strong hardware to process this information at runtime. Instead of doing this, I compiled the code. So it's binary instructions, assembly language that is going to the processor, so it's running natively. This ladder editor, it compiles this code in a C++ file, a header file, that is included with the firmware of the OpenPLC, and then everything is compiled using a GCC compiler, and I end up with a binary file. This binary file is small in size and fast. It's uploaded to the processor memory, and then it runs brilliantly and very fast. That is the OpenPLC. That's the project that I want to create to break those two barriers, to break the knowledge and cost barrier on the automation industry. It is a low-cost solution for automation, since it's free for anyone to use. You just need to enter in the website and download all the files, all the schematics. You can build your own PLC, or you can even use other solutions, for example, Arduino or other standardized boards. I developed software that support this kind of thing. So you can use the software solutions for the OpenPLC with other cards too, not only the original OpenPLC hardware. It also was made with a low cost in mind, so it was made with easy to find parts and cheap parts. That's why I went to the goal of having a cheap processor that, even not being fast enough, with a few tricks, it could get to have the job done. And I wanted to spread the knowledge, since I know that from the place I came, it's hard to have access to knowledge sometimes. And I wanted to make it publicly available all around the world. The code for everything is on GitHub, also on my website. It's openplcproject.com. And I have a few contributors around the world, people from Canada, people from India, that is helping to develop this idea and to improve the quality. And as I said, it's collaborative. So if there's anything on the project that it's not there yet, you can develop. As engineers, you can just understand how it works, how the OPLC protocol works, and create, for example, a new expansion card that is for analog input and output. And it will fit perfectly on the system that is already developed. So that's my project, that's my presentation. Thank you. So there are a few minutes for questions, I believe.
We have about a couple of minutes for questions, definitely.
What's an example application for this?
Oh, good question. I forgot to mention it, but my final undergrad project on the university was to replace the PLC that was embedded on a machine on the campus. It was a Siemens PLC. It has a very simple ladder program. It was an elevator. And then I printed out the ladder diagram for this. I insert that ladder diagram on my compiler, compile it, and replace the PLCs, and they both work exactly the same. Actually, there was even a bug on the original software that if you press 2 buttons at the same time on the elevator, it will stuck. And I figured out when I put my PLC on it, and I pressed the 2 buttons, and it was stuck, and I was, oh my gosh, it's wrong. And then before getting freaked out, I just replaced the PLCs, and I figured out that both having the same problem. The Siemens also had the problem. So the problem was on software, and I corrected it, and it's working exactly the same for the Siemens and for the OpenPLC. I'm looking for industrial application. Actually, I'm working right now with an industrial application for this project with a real industrial environment, and I believe it will be succeed as well.
We have time for one last question.
I didn't attend the complete presentation, so I may have skipped some parts in the beginning. But I know PLC software like Entertron, Sematics, Siemens, and there's PLC Edge. They also have like open kind of platform for programming. How is this one different?
Well, the other brands of PLC usually they can have open software for programming, but not open hardware. This project is completely open, from the firmware to the hardware, and for the software part, everything is available. So that's what makes it different. The low cost is not only for the programming cable, but also for the software and for the firmware. You can understand and have really the entire project in your hand.
Let's thank our speaker. While Daniel gets